Now I want to show you how to make a decision tree like in that robotic surgery study where we compared two different robots. And you can see me just go through the configuration and click through all the different steps like I did last time. Willingness to pay, remember, we just like to set that at $50,000, sort of traditional value to use for that. Right side is willingness to pay threshold. You can see me put the names and everything here. So I'm going to show you how to use a decision tree, but also how to do a sensitivity analysis, which is how we address uncertainty. So these are those two chapters in the book, Chapter 9 on decision analytic modeling, I think it's called, and then I think it's Chapter 11 where they talk about uncertainty and how we handle uncertainty in these models. So now you can see there's these new green circles. So remember, blue square is a decision, that's something we choose. And then a green circle, that's a chance or a probability. So the chance node is something nature decides. Right? So the blue square is what we decide between those two robots, and the green circle is what nature decides. So if we choose robot A, we're going to have two branches, two terminals, two of those red triangles split off of that green circle. So now you can see the first branch we'll just say is robot A with a hemorrhage. So we choose robot A, and then there's just 50% chance that there's a hemorrhage. Half the time there's a hemorrhage. And you see the cost and the quality associated with both choosing robot A and then subsequently having a hemorrhage as a result of surgery with robot A. And what's this other one? Well, this other one is no hemorrhage. So you could just see me go label it as no hemorrhage here. And the probabilities coming off of a chance node, coming off of green circle, have to sum to 1. So if hemorrhage happens 50% of the time, then no hemorrhage happens 50% of the time. So half the time there's a hemorrhage, half the time there's no hemorrhage. And in my other slide by hand, you could see how that top branch for robot A, that'll just be a weighted average between those costs and the qualities for hemorrhage and no hemorrhage because those probability weights are equal. They're both 0.5. And then you could see robot B, similarly, there's some probability that there's hemorrhage associated with choosing robot B, and then some probability that there's no hemorrhage. And so you've got these 4 different terminals, these 4 different red triangles, choosing between 2 robots, and then for each robot, some chance there's a hemorrhage and some chance there's no hemorrhage. Now, to incorporate uncertainty in the model like they talked about in the book, I want to code the probability of hemorrhage for robot B as a variable. So instead of just putting the probability in directly, let's make a new variable, and we'll call it the probability of hemorrhage for robot B. So we're making a variable for probability of hemorrhage for robot B. You can see me just label it, write a description there, and then we're going to set it to 0.25. So we could just write 0.25 in the tree instead of going through all this variable creation. The reason we have to make it a variable is because then later we could do additional analysis on the uncertainty like they talk about in the Chapter 11 of the book. So you could see now for this bottom branch, that's probability hemorrhage B. And then if there's no hemorrhage, remember they have to sum to 1. So that's going to be 1 minus the probability of hemorrhage B, because the probability of hemorrhage B minus the probability of hemorrhage B plus 1, 0 plus 1, that's 1. So those have to sum to 1. But you can see I just analyze it like a normal decision tree before. What it does is, since we set probability hemorrhage B to 0.25, as you can see on the left, it just plugs in that value and solves it. So you can see the ICER there, $20,000 per quality. That's less than the willingness to pay of $50,000. So when we roll back the tree, it's going to choose robot B. It's going to choose robot B right there just because we saw the slope of the supply curve, or the ICER, the incremental cost effectiveness ratio, was less than the WTP, or willingness to pay, we said at the beginning. Now undo that rollback just so it'll let us do a sensitivity analysis. So you can see here is we're going to define a range for probability hemorrhage B in intervals. So the probability of hemorrhage B, let's let it vary from 0 to 1, and then have 10 intervals. So here you can see the 10 intervals here. So what this is doing is it's showing you that slope of the supply curve for different values of P hemorrhage B, different probabilities of hemorrhage that could be associated with robot B. So that's now we have all these different ICERs. Then I'll click net benefits threshold, and you can see here what it does is it puts probability hemorrhage robot B on the x-axis, net monetary benefit on the y-axis. Remember, net monetary benefits are good. Higher net monetary benefits are preferred. So this threshold is 0.375. If the probability of hemorrhage for robot B is less than the threshold of 0.375, we choose the higher one. We choose robot B, where that red line's above the blue line. If the probability of hemorrhage robot B is larger than that threshold, then robot B is going to be too dangerous, and we choose robot A.